Okay. Thank you very much, Paulo, for the invitation, for organizing everything. So I was told, like Rita was told yesterday, to try to keep this general insofar as possible to make it accessible to the broad range of people who are here. So I've tried my best. We'll see how it goes. So this will be a talk. Again, Rita went over a lot of this area, I guess, introduced the ideas. I'm coming at it from a slightly different point of view. I guess Rita was coming at it more from the algebraic geometry point of view, whereas we'll come at it from more of a differential geometry point of view. But we're still working on the same two sides of the same thing. So again, Rita introduced quantum groups yesterday. I'll try to introduce a very hand-wavy, sort of not so technical, maybe introduction to these things. So maybe we just start off with the idea of a quantum integer. This is something very elementary that you can explain to somebody, a school child. So you're just taking this series here, and it's giving you what you would call a Q deformation of the integer. So of course you see, well, if you look just at the second presentation, when Q goes to 1, this will just reduce down to the integer n. Okay, it's reasonably straightforward. Why would you consider such things? Well, they arose first, I guess, in this form here, where you see, once you have your Q integer, this Q deformation of your integer, then you can mimic, or you can generalize the usual definition of the binomial coefficients, just like this here. Okay, and these arose originally in the work of Gauss, although I heard a talk in Prague a few months ago where somebody claimed that it even went back to the work of Euler. So then the joke kind of is that Euler and Gauss already knew about quantum mechanics. They have amazing properties, and starting off from the integer to binomial coefficients, you can keep on going, and you have fascinating structures, things like Jackson's Q derivative, Q integral, you have Q exponentials, you have the general theory of Q integrable or special functions. This somehow relates ultimately to integrable systems and so on, but there is this amazing combinatorial thing that arises naturally, that arises before any quantum groups, any quantum mechanics, anything like this, just this very natural thing to consider. If you get bored, an exercise, you can try to figure out what this is. How does additivity of the integer behave? Yeah. Can you find what's over here on the other side? Now, okay, so we have this deformation of the integer, very natural thing around for a very long time. So let's put that aside for 1 second. And let's go on to semi-simple Lie algebras, okay? So I don't know how familiar everybody is with Lie theory, but if you're not so happy with Lie theory, then just take G to be SLN plus 1 will match the rank. And remember, these are just the trace-free matrices. And in fact, for the talk, the work that I'm presenting, the new work that I'm presenting here, will basically be all about this here, which I will refer to as the A series. Again, if you don't know something about Lie theory, then there's a classification of these complex semi-simple Lie algebras into 4 families, which are A, B, C, D. Your SL, SO, SP, SO, and then there's a family of exceptionals, this finite family of exceptionals. We won't need to recall so much of the theory, but what we will record is that in some ways, and this is, Rita was saying yesterday that, yeah, we all learn when we're learning Lie theory that if you understand SL2, then you understand everything. What I've also been trying to teach the students in Prague is that, especially in the finite dimensional case, the complex semi-simple Lie algebras, or SLN if you prefer in the special case, they're integer structures somehow. The integers appear again and again. So there are values that will appear in their representation theory that, you know, should be real numbers, but are always fixed into the integers. So there's you come on when you go more towards the classification of these things, and you end up in these things called root systems, and the integers are always present inside in the root systems. So that the integers are somehow at the heart, at least in the finite dimensional case, the finite dimensional representations, they're at the heart of these Lie algebras. So we've got this amazing structure of Lie theory, of complex semi-simple Lie theory, which is very integer-like. And then we have over here this Q deformation of the integers. So you could naively try to bring these two things together and try to Q deform Lie theory by replacing the integers in Lie theory by quantum integers. Okay. So it might sound like a very naive idea, but in fact it works. And here is the presentation. This again is one of these things that if you haven't seen this before, you're not going to get much out of it. But it's good to present it at least to see it for the first time. In fact, yeah, maybe I did even learn it from being exposed to it numerous times again and again over talks. So maybe it's not fair to say that you don't get anything out of it. So what is going on here? What is going on is that we've taken our Lie algebra G, and this thing is a Lie algebra, so it's non-associative. Non-associative algebras are difficult to deal with. So what's one of the tricks is that you take this universal enveloping algebra. And this is rough. It's an algebra that envelops it. So G, of course, embeds into here. But this thing is an associative algebra. So it's somehow this way of, it's much bigger. This is infinite dimensional, whereas this is finite dimensional. But it has the advantage of being associative and make it easier to work with. And the representation theory of this, the Lie theory representation of this is the same as the algebra representation of this. So it's a much nicer object to work with. These things do not Q deform. So this process, I guess, this naive guess I had of taking the integers and Q deforming this thing will not work. But this associative generalization, this associative enveloping algebra, this actually does Q deform. And these generators and relations presentation of this is a Q deformation of the generator and relation presentation, the due to Serre, basically. The Aij is the Cartan matrix. This is the thing that can be used to classify these semi-simple Lie algebras. And you see here the Q integers are coming into play because these are the binomial coefficients. Don't worry about the details of the subscripts of the I and so on, but there you are. This is how to take your semi-simple Lie algebra, more correctly, the universal enveloping algebra of your semi-simple Lie algebra, and to Q deform it by taking Serre's presentation of the universal enveloping algebra and replacing all the integers with Q integers, basically. So these things are amazing. They're beautiful structures. They're dual to the quantum matrices that Rita was talking about yesterday. Okay, we'll come back to the quantum matrices a little bit later, but for the moment, let's just look at this. So the presentation that I gave of taking Q integers in the universal enveloping algebra is definitely not how it was invented. So maybe some proper mathematical justification for why these things are important. Well, let's look at some properties that they have, some amazing properties that they have. The category of finite dimensional representations, so the representations of this or this, it's equivalent. This is labeled by weights, these things related to your root system and so on. That carries over directly to the non-commutative setting, to the quantum setting, okay? Your category of representations is the same. This guy has got, well, the quantum version, Q of G, this has got a Hopf algebra structure. If you don't know what a Hopf algebra structure is, it's basically an algebra such that you can take tensor products of your representations, roughly speaking. It's an algebraic structure that's sufficient to allow you to take tensor products inside in your category of representations. Okay, which means that we can take tensor products inside here, which means that the category of representations is monoidal. Monoidal being just a categorical word for saying we can take, there's a notion of tensor product inside there. But the monoidal structure here is not equivalent to the monoidal structure of the original category. And that's what makes this thing interesting. I mean, up to here, if it continued that everything was the same, of course, there wouldn't be much point in actually formulating this Q deformation. But you get a new monoidal structure. And this point is quite subtle. And it's sort of the reason why these things are interesting. And roughly speaking, it's the unique Q deformation of the monoidal structure here. So the relations that I presented here, they're not unique. There are different ways of doing this, but the category that you have, this Q deformed monoidal structure that you have in your category of representations, this, roughly speaking, is unique. And then you have different ways of realizing it. And the relations that I gave, the Drinfeld-Jimbo deformation, these are somehow the simplest ones. These questions are related to Poisson structures, but again, like really yesterday, I don't really understand Poisson structures so well, so I won't dwell on that very much. There have then been many applications. So one of the most celebrated is that people are looking at invariants of manifolds using quantum groups, and they're related to knot theory because they're related to the Braid equation. So they're ways of producing very important invariants of manifolds. This is the work of Turayev, for example. Also, something that will be related to today, it's the theory of canonical bases. And this is an application to the classical representation theory, a genuinely quantum application of the classical representation of the quantum groups to the classical representation theory of your semi-simple Lie algebras. Also things like von Neumann algebras and Jones polynomial and so on and so on. So that there are things that sort of arose out of integrable systems, but have found a huge number of applications since. So let's though go back to this question here, okay? Your Lie algebra embeds into your enveloping algebra. So and they found back in the 1980s, this deformation of the universal enveloping algebra. So one would guess that all of these years later, the question of what the quantum Lie algebra inside here is would be solved, would be done. But in fact, there are various guesses, one in particular by Majid, but there's no generally accepted question. And this is a very subtle question that maybe doesn't receive as much attention as it should, but we do not understand what the Lie algebra is inside there. It should be that it's some sort of a Q deformation of the Lie bracket and so on, but finding this has up to this point eluded us. What we do have though, this won't work even then, because I mean, it's a good question, no, but if you look at just this is the E tensor K and 1 tensor E. Even the generators here are not primitive because of the K. So what is the primitives form, Elisa? But it's a good question. I should know the answer. Maybe it's just too small. That would be my guess. Yeah, my guess is that it would be too small. It's not going to work. No, I mean, it's a natural idea, but no, it won't work. Proof by, if it had worked, it would have been done by now. What we do have, though, is we have this Poincaré-Birkhoff-Witt. Okay, so if you don't know what that is, it's a sort of the theorem that spawned a whole family of PBW. This is what it's contracted to, of PBW theorems. And what it says is you take the usual basis here, the root vectors. So this thing has an action of a torus, it decomposes into root vectors. And you take these things and you can formulate a basis of this from the root vectors inside here. We'll see in a little more detail what this is like in the quantum setting. And this is hugely important for the structure of U of G. So any Lie theorist, that's kind of one of the basic tools they will go to when they're trying to prove anything about U of G. So what Lustig did was, being the smart guy he is, tried to formulate a generalization of the PBW theorem for the quantized enveloping algebra in the hope that that would then be used to prove as many theorems as it is in the classical case. So how does he do this? Well, he took an action of the braid group. So for those of you who don't know what the braid group is, let's say in this case, what we're looking at is the Weil group of these things. So from here on, we can probably just specialize to the A series case. So if you look at the Weil group associated to SLN, it's just going to be the symmetric group, okay? The usual symmetric group we all learn about in undergraduate. If you take the symmetric group and you look at the relations that are inside here, one part of the relations of the symmetric group is that SI squared is equal to the identity. If you remove this, then you get the braid group, okay? What you're left with are the braid relations and the relations where they commute if they're far enough apart, if that makes sense to you. But that's somehow a very important point in the consequence of going from the classical setting to the cuneiform setting, is that this relation disappears. It ends up that when you perform operations that in the classical setting would get you back to where you are, you're a little bit different from where you are. Maybe because they're physicists, or I could make the analogy with an electron. When you turn it around once, it's not enough. You have to turn it around twice to get back to where you started from. I don't know if that helps. So what he did was he took not the symmetric group, but the braid group, and then formulated an action of the braid group on this quantized universal enveloping algebra. Okay. Again, these formulae here, you're probably not going to get so much out of them, but you see the T's here. What are they? Well, you're getting quantum integers on the replacing. So it's effectively a generalization of a classical formula where you're replacing integers by quantum integers, but the proof is quite technical, not conceptual at all, and it's just a bad calculation. So this mapping, sorry, the WI here should be an S sub I. I'm going to denote, because it's the symmetric, it's the braid group of the symmetric group. I'm going to denote the generators by S sub I. So if you see a W again, it should be an S. This determines an action, so it's an algebra action of a braid group on the universal enveloping algebra. Okay. How does that get us to this PBW theorem that we're trying to prove? Well, we take this definition here, we take, and this is kind of a crucial point, we take a reduced decomposition of the longest element of the Weyl group. If we're in the A series, our Weyl group is just the symmetric group. So we know this is a finite group. We've got a longest element because we have a well-defined notion of length. And we could take the longest element, but there's a number of ways to present the longest element of the symmetric group, or in general, the Weyl group. What you do is you make a choice of reduced decomposition. Okay. Okay, that's a typo with the subscript of G, you mean? Yeah, it's because the braid group depends upon the series. So if you're in the A series, your braid group is the symmetric group. If you're in the B series, it's a semi-direct product of the symmetric group with Z2, I think. In the C, it's the same. In the D, and then you go to the exceptionals, and it becomes these crazy, groups with an order of 1 million and something like this. But yeah, it does depend. But the process of passing from the braid group, sorry, the Weyl group to the braid group is always the same. You always remove this because this relation is always inside in the braid group, no matter what the series. In fact, this is a statement about Coxeter groups in general. You have a braid group corresponding to any Coxeter group. But thank you, a good question. But you also pointed out a typo. So the B here, unfortunately, has gone into the frac. That should not be the case. Okay, so sorry, yeah, let me back. What you do is you take a choice of reduced decomposition of your Weyl group, or the symmetric group in this case, and then from this, it gives you a recipe to construct root vectors. Okay, positive root vectors or negative root vectors. So this Lie algebra will always decompose this triangular decomposition into a positive part, into the cartan in the middle, and into a negative part. Okay, your E's, your F's, and your cartan in the middle. What this is doing is giving you a recipe for this part and this part. So we don't know what the quantum, sorry, I guess maybe I should write the Q here. It's giving you a recipe to prescribe this and this, not the middle. And that's going to be crucial to what we're going on to. So from this, we then get our PBW theorem. So these are the root vectors, the quantum basis, I guess we have this quantum guy and this guy here. And then the K's that we had earlier on in the definition of the universal enveloping algebra, we're sort of sticking them in. Okay. And this gives you a basis, a linear basis, a genuine linear basis of your universal enveloping algebra. And from this, you can take a lot of the proofs that you have here classically, and you can extend them up directly. For example, Verma modules would be an immediate application to these things, if that makes sense to you. And from this, then, consequence that came is this canonical basis theory that I was talking about earlier on. One of the major applications of quantum groups to representation theory, classical representation theory, is that from this quantum PBW theorem, you can produce these amazing bases of your finite dimensional representations that have fantastic properties with respect to tensoring and so on. And this is a hugely important thing. And this is kind of a milestone in the study of the theory of quantum groups. Okay, so far this has been a talk about representation theory. Try to do some geometry, non-commutative geometry. But before we do this, let's look at some examples. Just so you get a feel for what's actually going on. So this is reasonably abstract. So if we look at the case of SL2, everything is quite easy. In this case, your Weyl group is just going to be the symmetric group of order 2. So you've got SL2, it's got two elements inside there, it's got the identity, and it's got the flip. So this is the symmetric group of two objects, because if it makes sense, your root system is going to have two things. And this whole recipe here, so the choice of longest element, there's only one, it's S1, that's it. And then this procedure, if we do this Lustig procedure, what do we get? We just get the single element E. So remember in the definition, that complicated definition I gave you at the start, we have generators for the quantum guy, we have generators EI, KI, and FI. So the positive part of this is just going to be in here, will just be the single E. There's no subscript because it's just one. Okay, let's see, things get a bit more interesting when we go up to SL3. So in this case, the vial group is just going to be S3. And if you think about it, so that means we're going to have these two generators, and the longest element of the vial group is going to be S1, S2, S1, or through the braid relation that is in the symmetric group, S2, S1, S2. So we have two choices. So that means then that we're going to have two associated quantum Lustig root systems of root vectors, two associated PBW theorems. What does that look like concretely? Well, you've got E1, E2, E1, E2, the simple guys, the generators don't change. And then this choice of decomposition gives you either a commutator for Q inverse or a commutator for Q. And of course, we see that as Q goes to 1 in the classical limit, this is just going to reduce down to the usual commutator. And this is what the positive root vectors are for SL3. You just got these two simples. If you think about it in the upper triangular matrices, if that helps, you're going to have, and this is too big, kind of E1, E2, and you got your commutator here. Okay, so this is just the zeros here. Okay, if you take the commutator bracket of the two of these, you get a 1 up here. And that's what's going on. Okay. Let's go up to S4 or SL4, and then things become more complicated again and more interesting. So we see that these are, we've got 321, 323. That's the sort of one of the nicest decompositions. And dually over here, we've got this 1, 2, 1, 2, 3, 1, 2, 1. And then in the middle, we've got these ones that are more mixed up somehow. Okay. One thing we should notice about this, no, so this slide seems to be missing, is that we've got a symmetry of our symmetric group that basically sends 3, right up here. It sends 3 to 1, that sends 1 to 3, and it sends 2 to 2. Okay, this is just an automorphism, because if you look at the relations of the symmetric group, these are just labels, and you're somehow switching the labels. If you think about it in terms of the Dinkin diagram, if that makes sense to you, we're in SL3, so it's going to be the thing that goes like this. You've got basically nothing should change, nothing will change with regard to these. It's just a switch of the labels, and that gives you. So if you take this diagram here. This gives you this kind of isomorphism. You check here in this diagram, okay? Is everybody okay with that? Or you can see perhaps that I'm not telling you the entire truth, that if you perform this swap here, it doesn't quite work. So what I've neglected to tell you is that these root vectors that we have, this space of root vectors, they don't actually depend on the nose on the reduced decomposition. They depend upon the reduced decomposition up to commutation, a commutation class, which is to say, if we look again at the symmetric group, if I have I minus j is strictly greater than 1, then I can always commute these things. Okay, so we've seen before, we've now got, I guess, all three of the relations. So this is the relation, this idempotent relation. This is the relation such that if your generators are far enough apart, then they actually commute. And the braid relation was on the previous slide. They're the three relations of the symmetric group. And I guess it's this and the braid relation that's left in the braid group. And basically, the reduced decomposition doesn't see this. So if two decompositions, so you can see here that, let's say in the middle one, okay, this guy here, if you perform this operation, you'll then need to reorder swapping the 3 and the 1 in order to get back where you started. Okay, so the lesson is that it does depend on the reduced decomposition, but more precisely, it depends upon the commutator classes of the reduced decomposition. Reduced decompositions up to this relation. Okay, so what that means is that I can now forget about what's happening on the right-hand side of this slide, which is also convenient because it's extremely difficult to fit it all into one slide. And then we see what the reduced decompositions are. Again, to fit it on the slide, so the subscript of a minus means q to the -1, the subscript of a plus means q to the 1, just to fit it into the slide. And you see that for the first one here, the decompositions are kind of coherent. And as you go along, it becomes more and more incoherent and some are more badly behaved. And the idea that we have here is that maybe we can try to probe this and to see the combinatorics that are occurring in the quantum setting using a non-commutative geometric argument. Okay. So for that, let's recall a little bit of classical geometry, I guess the geometry of flag manifolds. If we have this cartan here, well, let me go back to this. This cartan inside here, if we look at the dual group, so in the case of the A series, this is going to be SUN, we're going to have a torus, a maximal torus inside. Inside our group, and if we quotient by this and we look at the homogeneous space, this is what's called a flag manifold. Okay, we'll define it in the quantum setting more precisely in a second. But in that case, what you do is when you quotient, as we know, if you take a Lie group, you quotient out by a subgroup, you get a homogeneous space. What happens over at the level of the Lie algebra is that you take the Lie algebra of the group and then you quotient out by the Lie algebra of the subgroup. So in this case, the Lie algebra is going to be the Lie algebra of the maximal torus is going to be the cartan part. So this guy disappears. That's what happens. And you're left with these positive and negative parts. So what I'm now going to do is, simply because this is what we have calculated up to this point, I'm also going to get rid of this. And we're going to treat this part as if it was part of the tangent space of a quantum flag manifold. That's roughly the idea. Okay, so this is just the exact sequence that you would get classically. And this T01, this is because all of these flag manifolds classically are complex manifolds. So we have a decomposition of our one forms into holomorphic and anti-holomorphic. And we're just going to look at the holomorphic part, the anti-holomorphic parts. Okay, so this is the classical motivation. And just like, can we find a quantum generalization of this? And can we use differential geometric ideas to probe Lustig's construction, to probe the combinatorics of the decomposition of the longest element of the Weyl group? Because the difference between the root spaces and the BBW theorems and so on, that happens because of the choice of reduced decompositions is really not something that's discussed very often. And we were trying to see if we could examine this using geometric ideas. So let's just go back. I gave you the rough idea of what a full quantum or a flag manifold, a full flag manifold is just a quotient of the group. Let's say in this case, SUN by the maximal torus. Let's just give you the quantum generalization. So the flag manifold is OQ of SUN. Now I haven't defined OQ of SUN yet, but fortunately Rita did it for us yesterday. What I can do very quickly though is to say, how would you define it from this? Basically, you take the dual Hopf algebra, okay? There are subtleties involved here. But that is roughly what's going on. You take the dual, and what this does is it gives you a Q deformation more or less immediately. There's this construction is not difficult. More or less immediately gives you a Q deform of the coordinate algebra, the representable functions on the associated connected, simply connected, compact, semi-simple Lie group. Semi-simple Lie group. And that's what this is here. We've now completely restricted to the A series, to this SLN. Dual to this is SUN, and unfortunately, this is SN plus 1, and this is SN. So I'm after mixing up the indices, but I guess it couldn't. So what we do is we take this cartan part. This is the thing that's going to be generated by the Ks, okay? It's sort of the quantum cartan part, this U of H, maybe I should write this. So U of H is just going to be, you can put a Q, sometimes you do, sometimes you don't, generated by the Ki's plus minus 1. Okay. And then we look at the space of invariance of this. Okay, so we're going to do those functions that are not going to see the action of the cartan. And if you think about it, again, classically, this is going to be the same thing as the algebra of functions on the space where you're quotienting out by the torus, okay? Or you can just take this as a definition if you want. What this does, though, and this goes back to Masood's comment about primitiveness, is that we're now going basically into a quotient by the cartan. So then this thing disappears, roughly speaking. So somehow, looking at your flag, elements that were not primitive before kind of become primitive. And that's why things work a lot better. So I guess you could see this coming. And that's what going on. What's important here, though, is we're quotienting here on the left, Julie on the right. So then that means that we're going to have an action on the other side by UQ of SL or a coaction by OQ of SUN, whichever way you want to see it. But there's a symmetry on your algebra in the same way that if you have a group and you're going to quotient group over H, you're going to have an action by G here on the left. Okay, that doesn't upset the cosets, and this is the same thing. And we want everything to respect this. So now the question is, can we build, going back to this geometric idea, can we build a differential graded algebra? So this is a differential graded algebra, going to be a graded algebra together with a map satisfying the Leibniz rule, graded Leibniz rule, something that basically generalizes the properties of the de Rham complex of a manifold. Can we find one of those for these flag manifolds coming from this viewpoint of these guys here being I should really have written this as N, I guess, being the tangent space, quantum tangent space. So for time, maybe I should start to speed up a little bit. More formally, for those of you who know something about Hopf algebras, we're going to try to look for a differential graded algebra such that each part of the graded algebra is going to be a relative Hopf module. So it's something that's going to have a coaction of SUN, and it's going to have a module action on both sides, a bimodule structure over the algebra. This is something that works because we've got this categorical equivalence called Takeuchi's equivalence, which is basically a Hopf algebraic generalization of the notion of an associated vector bundle, as was asked about yesterday. So these are quantum homogeneous spaces formally, whatever that means. And it means that for when you have the quantum subgroup, for every representation of this, for every comodule over this, you're going to have a corresponding quantum non-commutative associated vector bundle. And this works very nicely, a direct generalization of the classical setting. And we're going to be doing it in this context, okay? So what we're going to do is that it should give a little more explanation. Is that we're going to take a module over, thank you. So wait a second, sorry. We're going to take take the category of modules over the cartan, the quantum cartan. We're going to consider this guy as living inside here. I guess I'm using both notations. And then from this, we're going to take an associated quantum non-commutative associated vector bundle from this. It's a direct generalization of the classical construction of associated vector bundles over a homogeneous space. And this is sort of the categorical framework that is there to take care of this. So this has been formally laid out. So let me just recall the results. It's that this thing here, this process is for constructing a vector bundle, a homogeneous vector bundle, an equivariant vector bundle from the representation. We want more than this, though. We want to construct first the tangent space. So this has got more structure. And what extra structure does this thing need to have in order for us to be able to consider it as a space of tangent vectors? Well, this has already been thought about for a long time. I guess, first of all, I'm missing Voronovich, who was the guy who first thought in this direction. This is for the level of the Hopf algebra, and then generalized to the level of quantum homogeneous spaces. It was done, and I'm going to state the result here just for the case of the quantum flag manifolds, okay? The second condition here is basically immediate, because from Lustig's construction, everything is going to be a weight vector. So that's basically when you're a module over the torus, that's the same thing as an eigenvalue over the Descartes time, which means that you're a weight vector. So that one is taken care of. So the condition that and the first one is basically formal. So it's the middle one here. We need to check that this, maybe I should have a Q here, that this thing is actually co-ideal in this sense, okay? And that's the one that we're going to check, because this thing here is dependent again on the choice of reduced decomposition of your Weyl group. So this is the thing that we're going to, it's this condition here in the middle, that's what we're going to use to probe these decompositions. Now, if you have this, then, okay, just as I've written here, you're going to be able to define your tangent space, your tangent vectors to be this space here, and then we're going to perform a dual construction where, okay, take my word for it because time is ticking, that we can dualize this inside in this category. You can just take the dual module, and this dual module then has the amazing property that we have a map that goes from our algebra into here, and this satisfies the Leibniz rule. So there's a lot going on inside here, but I guess the point is that if you have this condition here, pointer, if you have this condition here, if this is satisfied, then you can construct quantum deformation of your one forms, okay? Going back to our examples for SL2, it's clear that it works. In fact, the proof is already here. For SL3, things become a bit more complicated. Sorry, SL2, this is SL4, sorry, yeah. And now we actually see that at this level, the non-commutative geometry of these things actually sees the difference between your reduced decompositions. So what do I mean here by left and right? What we did was when we took the quotient, we were quotienting on the left, or dually, I guess we're quotienting on the right. We've made a choice in which way we're going to quotient by the torus, by the non-commutative torus. So that's why if we go back, our condition here on the co-ideal, it's chosen aside. So you want it to be to the left. But we could have done it on the right, and everything, there's no reason to choose one over the other. And what happens is that for these decompositions here at the end, these ones that were quite nice, the ones that were somehow the most coherent, they actually work whether you quotient on the left or whether you quotient on the right. They're that well behaved. And then these ones in the middle, these more incoherent ones in the middle, they will only work, some of them for left and some of them for right. So already we're seeing that these reduced decompositions, some are better than others. If we go up to the case of SL5, then things become even more interesting or complicated. So here you've got something like 62 classes of reduced decompositions. It's impossible to fit them all up here. So I'll just give you the first couple in this. Again, they form this sort of picture, like the picture up here, where it becomes larger and then it becomes smaller again. And you have this same symmetry as I've given up here. So you will have a dual of this picture over here and lots of complicated things that are appearing in the middle. Okay, so these are the decompositions themselves. How do the positive root vectors behave with respect to this? We saw that when we went for SL2 and SL3, everything worked. For SL4, we saw that we were already getting some reduced decompositions that were better than others, but they were always giving us tangent spaces and they were always giving us these quantum one forms. So what happens in this case is that we see again, these guys, the left is always the best behaved, and dually the other one on the other side. But we get things that are left and right, and then we get ones in the middle that do not satisfy this co-ideal condition at all, and will not have any associated geometry from this tangent space setup. So it's already starting to probe the difference of these things. And that's why then from now on, basically, we're going to, so we conjecture, we're trying to figure out that somehow all of the ones that are not at either end are basically not the good ones to choose, and that these are somehow canonical. And these are the ones now, these reduced decompositions, that we're going to restrict our attention to for the rest of the lecture. So when did we start? 20 minutes more. Great, that should be okay. So as I just said, we choose to restrict your attention now to this decomposition. Unfortunately, this should be, well, this is S, I'm mixing between S and W. And it's dual, which is to say those reduced decompositions that are nice in the sense of Peter Littleman. So if there's any of you know some combinatorics, Littleman has studied, and combinatorialists have, the symmetric group, of course, the reduced decompositions have been studied for a very long time. Littleman then, and these two reduced decompositions that we have found to behave nice in the non-commutative geometric sense were already very well known, of course, for a very, very long time to combinatorialists as being somehow distinguished. Littleman decided to extend this to the other series, to the other braid groups, formulating a theory of nice decompositions. So this is what we expect will happen in the other series, but or maybe we should move on and not dwell on this. But the next question is, we've just got the one form, so we wanted a differential graded algebra. Now we've just got the one forms. And in fact, there's a very general construction here that if you have one forms like this, so you have a module over an algebra, and you have a map from that algebra in such that it satisfies the Leibniz rule, just as we had in the previous slide, then this can be extended to a differential graded algebra. And there is a unique differential graded algebra, universal differential graded algebra, that is maximal in this sense, which is to say, if there's any other extension, then you've got a projection onto this. So basically saying very quickly is that from this, once we've constructed this, this was the hard part, constructing the one forms. Then from this, we get a whole differential graded algebra basically immediately. Okay. And this construction, if we go back down to the classical case, this universal maximal prolongation of your one forms actually reduces down to the exterior algebra. So, which is to say, definitely in this construction, you will not have Grassmann relations. They will not swap. But it is somehow a uniform construction that in the classical case does give you, in the commutative case. In this case, yes, and that would be in the previous slides. But I guess this construction I'm saying here works for any algebra. You take tensor products and you take quotient. Exactly. You take tensor products and then you quotient by the bimodule generated by this. Yeah. I didn't want to say this because then I have to give the universal calculus and then I have to give this and so on and so on. But so before, but as Masoud said, in this case, for our calculus over the full flag, we are in fact going to get Q-deformed Grassmann relations. And they admit a very nice Lie theoretic, a very compact Lie theoretic presentation. But before that, I'm going to give you a little bit of Lie theory and root systems and how we can order root systems. For those of you who maybe don't know enough about the Lie theory, you can just zone out for a while and come back a little bit later. But there is a, as we know, in any root system, we've got a partial order, okay? But, you know, partial orders aren't as good as total orders. So the question of how to put a total order on your root system in a sort of canonical way is something that people have been looking at. And it turns out that there is a particular type of total order on your root system, which is just here. It's called a convex order. So which is to say, if I have, let me just restrict to the positive parts. If I have two positive roots, and it's such that when I take their sum, this is again a positive root, and that alpha is less than beta with respect to the ordering that we've taken, then if alpha is less than alpha plus beta is less than beta, this is what we call a convex ordering. And it turns out that these convex orderings are actually in one-to-one correspondence with reduced decompositions of the longest element of the Weil group. So what we're going to do is, because we've focused on one particular reduced decomposition of the Weil group, or commutator class to be more precise, we have a corresponding total order on our root system. And it turns out very nicely that this total order on the root system is the one that allows us to give this very compact presentation of the Q-deformed Grassmann relations. Okay, so if you don't know much about root systems and so on, just say that the reduced decomposition that we've chosen gives us a very nice ordering on our basis root systems. So let's just look at it for the A-series case with respect to the order that we've chosen. If we, going back to, maybe I'm already after erasing it, but if you look, you think of it in SLN, these were trace-free matrices, so everything upper triangular, strictly upper triangular entries are going to be the corresponding root vectors of our Lie algebra, and I've presented them here. So the other part, lower triangular part of your matrix and the diagonal is missing because it's not relevant to what what we're doing. So if you just take this order, the bottom one, which is going to be the simple root E3, that's going to be lowest. Then we go up to this first commutator, and so on. And then you just take the transitive closure. So it should be a total order. So just fill in all of the rest of these to make it a total order. And that's the total order that we get. So you see again that, yep. I don't know. I don't. Maybe. Yeah. Yeah. So unfortunately, I'm working on the A series. Ali has moved on to the other one. So as he keeps, this is not in the Dinkin diagram. No. This is I mean, because on the Dinkin diagram, you're just going to get these guys here, the simple ones. So
see, the diagonal is your big.
Yeah, exactly.
You're moving along.
Maybe. I don't know the answer. I'm really after learning about these things reasonably recently, and I'm using them to give the presentation here. So I'd be happy to talk about the combinatorics a bit more. But now with this total order, we can now give a presentation. So there's a lot going on here at the start. So maybe I should first of all answer, what are these E's? Going back to this presentation here, okay, we've got, these are our tangent vectors. So then we performed the Joule construction where we had our omega, and this thing was going to be from this homogeneous vector bundle construction, or the non-commutative generalization, over this cotensor product. We have a T01. Okay, this is just the Joule to this inside in this category. This thing has got a basis of root vectors, quantum root vectors. So all we do is just take the Joule basis over here. The entries here are labeled by our weights, because we've got one weight vector for every, by our roots, we've got one root vector for every root inside in our root system, the positive part. So then dually over here, we're going to have a basis element for every element inside in the root system, okay? And it turns out that these cutiform Grassmann relations that we get depend on the relationship of the roots inside in the root system, which is very pleasing. So the ordering that we have here is the one that I spoke about before, the convex ordering given by the reduced decomposition of the longest element of the Weyl group that is giving us this thing in the first place, okay? And you see that, okay, so when it's E alpha, this goes to 0, as one would hope. In the other series, this does not happen necessarily, but in the A series, everything works out more nicely. Here, for the case where, now, you see, I've also got another ordering going on here. This is the partial ordering. So this is the standard partial ordering on your roots. Okay, and it's the interplay of the two of these, the total order and the partial order, that allows us to express the relations in this compact form. So if these things are comparable with respect to the partial order classically, with respect to the partial order on your root system, then you just get this very nice Q deformation of the Grassmann relation. And what's up here in the brackets, that's just the pairing of the two roots inside in the inner product of this root system, okay? It's the A series, so it's either going to be plus or minus 1. If you go up, though, and we find that these things are not comparable, classically, then it gives you somehow extra space for more quantum behavior to occur, and you get this extra term. Now, I'm sorry, I should have defined this before, but this is nu is equal to Q minus Q inverse, standard thing. So you see that when, this is a very common thing that appears in quantum groups, and when Q goes to 1, this thing disappears. So it's often you will get these additional quantum terms that appear, and they'll always have this as a factor, as a scalar multiplying in front. And that's what happens. We get this extra term over here with this alpha prime and beta prime. So what is alpha prime and beta prime? I'll show you in an example in 1 second. And yeah, I think that basically that's what I wanted. So yeah, eventually, yes, you're correct. It's a Q deformation of the exterior algebra, but one in a very subtle way interacts with the root system. Let's see what this looks like in some special examples. And then we won't, in the first case for SL3, for SL2, it's too simple. There's nothing going on. It's a one-dimensional vector space. So you just, the order 2 is trivial. Maybe I should also stress that what we're talking about here is I've taken this maximal prolongation construction that we have. Wait, sorry, this should be V01. This maximal prolongation construction that we have, it can basically all be done at this level, at the level of the inducing or co-inducing representation. So the relations that I'm giving here are for a finite dimensional vector space. So you'll see that if you want to go back to the actual forms themselves, you need to take these algebras that we have here, slot them in, and then that will give you the higher forms. So basically, because everything is at the homogeneous level, because everything is a relative Hopf module, I'm allowed to do everything inside in this category and make my life much easier. But these things are always there when we go across the equivalents. So here we see, now I've also, because we've dualized, it makes more sense, because we've dualized from the root vectors to from the tangent space to the cotangent space, everything is switched from upper triangular to lower triangular, okay? And in that case, we're going to have 3 root vectors, just dual. And the relations are just Q commutation relations, because if you look at the associated root system, everything is going to be comparable, so it works. Yeah, this is arbitrary in this case. Yeah, this is for this, yeah, maybe SL2, the first relation. No, yeah, because it's the dimension is too small. Yeah, and if you look at the corresponding root system, you see that everything is too easy basically for this to appear. But very good question. But if we go up to SL4, then it starts to appear. So there is, that should be SL4. Yeah, thank you. So now what we do is we're going to break up, our root systems. So we're going to break up our relations into positive and negative, depending on how the corresponding root is. And that gives us the relation. So we see that the roots here, when the relationship is that it's greater than 0, we're going to get a Q commutation relation. In this case here, we're going to get Q to the inverse. I've presented this with the directions the arrows are pointing in. So if it's pointing from one to the other, you get a Q. In the other direction, you get a Q inverse. Maybe that's not so important. But you'll see that for these root vectors, positive and negative pairings, we just get this Q commutation relation. And then if we go up to SL4, or sorry, we go to the ones where they're not comparable or comparable, we end up getting that in these cases, they commute because the pairing is going to be 0. But over here, these two guys here are the only ones in this order that don't actually satisfy this. And then this dotted line indicates this quantum term, this thing multiplied by this guy here. So these are the primes that I was talking about earlier on. And more generally, you'll see that this is going to happen when your 2 roots are like this, and the primes are when you just kind of complete the rectangle. That's the extra term that adds in. And it's again all due to you have this freedom to do this because of multiplicities of weight spaces and so on. But this one, it's this. Yeah, just this quantum term that's going to disappear. Okay, so we've got 10 minutes, so let me maybe then I'm going to skip Frobenius algebras. For those of you who know what a Frobenius algebra is, these things are Frobenius algebras. For those of you who know what the Nakayama automorphism of these things is, well, the Nakayama automorphism of this thing is classical. So this is one part of this geometric representation theory. We're getting non-commutative quantum geometric realizations of Frobenius algebras. But let me move on. Yeah. Yeah, it's not symmetric. Okay. It's symmetric. Well, this one. Yeah. Okay, I mean, if there's some interest in Frobenius algebras, maybe then I will go back. So then Frobenius algebra, your pairing, multiplication. If you see it presented like this, yeah. Yeah. And the motivation we're taking here is that the usual exterior algebra of a finite dimensional vector space, you take your finite dimensional vector space, you take the exterior algebra, you know that eventually over here it's going to be a one-dimensional space. what you do is you take two elements, and if the degrees are correct, the zero otherwise, but if the degrees are correct, if they match, they're going to land inside in the top part. And then, making a choice of volume form, that's going to be isometric. It's going to be isomorphic to your field, and you go over to your field, and that's what we're generalizing here in this presentation. So usual exterior algebra is a Frobenius algebra, and it's not symmetric because you've got a sign. It's symmetric up to a sign, but not symmetric on the nose. So then a natural question to ask is, are our quantum exterior algebras Frobenius algebras? And the answer is yes, they are Frobenius algebras. But what's interesting, though, is that the difference between it being symmetric, so if your bilinear form is symmetric, this is sort of captured in the notion of the Nakayama automorphism of your bilinear form. So it's somehow, because of the Frobenius property, you have this magic algebra automorphism of your algebra automorphism of A, that is going to somehow correct the difference of your bilinear form between your bilinear form being symmetric and not being symmetric. Just as is presented, here. So now our relations are these Q-deformed relations. So we really expected that what would happen is that when we looked at this, you would get some Q deformation of the Nakayama automorphism. And we started to do calculations, and all of these amazing cancellations started to occur. For first, SL3, SL4, and then at some point you're like, okay, something is going on. And there was quite an involved calculation going on, and it goes back to the way that the relations are presented in terms of the root system before. And then if you actually work at it for long enough, you can you find out that all of these amazing cancellations occur. This is a general phenomenon, and the Nakayama automorphism is like this. And this is actually the Nakayama automorphism of the classical exterior algebra. So these things are the same. So it's not symmetric, but it's as unsymmetric as the classical exterior algebra, which is something that we were definitely not expecting. But 5 minutes, less. Okay. So I'll go on, because there are people in the audience who did work on this initially, on looking at non-commutative realizations of representations, this Borel-Vey theorem. So I guess Johnny and Masoud did this, I don't know how many, 10 years ago at this point, something like this. So the question is, can their approach of realizing line bundles over your flag manifold and looking at the holomorphic sections, can this be extended to this setting? And the answer is yes, this extends directly to this setting. Okay, there's not time to define what this means, but you have line bundles over your full flag. That generalizes directly. They're modules, they're finitely generated invertible projective modules over the base. They're indexed by the same roots that there would be, weights that would be indexed by classically. They admit a connection with respect to the 0-1 calculus here that is flat, a little bit Leibniz rule, of course, it's a connection. And then you look at the kernel of this, which classically would be the holomorphic sections, and it's the same thing on the nose. And it so gives you a realization, not just of the representations corresponding to the cross node of the Dinkin diagram for CPN, or more generally, as I did with Ale, for the Grassmannians. This now gives you realization of the representations for every finite dimensional representation of UQG, this non-commutative geometric realization. There's a little bit of an explanation of what's going on here, but unfortunately there's not time. But let me go on just to the last slide. So for people who do know about what happens in the case of the quantum Grassmannians, which is a particular type of flag that lives inside in your full flag, this presentation, that's definition that we had of the full flag, quantum full flag before, this has a natural generalization to partial flags. You just need to generalize your Levy subalgebra here. Then you do the same picture. We have an inclusion when we have an inclusion of subsets of your simple roots. We can then restrict the calculus to these subalgebras. And for the quantum Grassmannians, which is to say you're just taking one cross in your Dinkin diagram, which at Q goes to 1 gives you back the function algebra of your classical Grassmannians. We recover this celebrated Heckenberger-Kolb calculus in this case. So I guess this is the point where I should be more honest and say, actually, when we started off with all of this, We were not interested in reduced decompositions of the longest element of the Weyl group. We didn't really even know so much about what Lustig was doing. I wanted to try to generalize this result, which is one of the most important results, and it extends to the other series, one of the most important results in the non-commutative geometry of quantum groups. We were trying to extend this. And then in the process of extending this, we came across all of this combinatorics and all of the quantum PBW theorems and the work of Lustig and so on. And this was going to be the final test that for whatever we did, it would have to recover this, and it does. Okay, so sorry, it's a little bit quick, this presentation of, for those people who don't know much about the non-commutative geometry of quantum groups, but it is an extremely important structure, and we wanted to recover this as a test, and it works. And you might ask, there were actually two decompositions that we had up to this symmetry, the one that we have here. Both of these reduced down to the same one. The difference between them disappears when you restrict to the Grassmannians. Next are some open questions, but I think at this point I've gone. Maybe I'll put the open questions. For those of you who know about Nichols algebras, we've managed to present previous work, the Nichols algebras, the Grassmannian exterior algebra as a Nichols algebra, and we're trying to extend this up. What is a Nichols algebra? It's something where you take a solution of the braid equation, and then you try to generalize exterior algebras in terms of this solution of the braid equation. What happens for the other series? This is what Ale has been working on. This is why he knows more about the complexities of the Lie theory in these other series than I do. And then, of course, there's the question, I erased earlier on this part. What happens if we try to do all of this? Well, we expect that everything works. It's just we haven't had a chance to calculate it yet. And what happens when we do this is that we get the entire, at least the complexified tangent space, and then the dual complexified one forms. And then that is extremely important because you get a very beautiful picture that has already been worked out at the level of the Grassmannians in the work even of Heckenberg and Kolb. And here we'll write it for CP2 for this low dimensional example. We would like to generalize this picture up here because when you do this, you actually get I already said that these manifolds classically are complex manifolds, but they're also Kähler manifolds. So you have a huge amount of structure on your Durham complex. It breaks up. So far, what I've been talking about in this talk has just been this piece here. But if we roll up our sleeves and continue to work and do this part here, we'll get this guy. And then, in fact, this whole double complex where there is much beautiful structure, Kähler structure occurring inside here. These, well, and that's basically where we're going. And hopefully we'll be able to for so long. And there I think I'll stop and thank you for your attention.
You mentioned that lambda cube was causal.
I'm
guessing that it's causal different properties.
Yeah, this is, I don't understand this so well, I have to be honest. This has been worked, there should be, so this, the Koszul joule has been worked out. If you go to the level, let's say the Grassmannians or the other reducible flags, this has been worked out, work of Matthew Tucker-Simmons and Uli Kramer in his thesis from about 10 years ago. I don't understand it well enough, unfortunately. This is a very interesting question. So we haven't actually calculated these relations in the other, and we expect, well, we don't know if you have classical dimension or not. So it may be, it might have less than classical dimension. I hope to have these calculations done before this talk, but no, it didn't work out. So, but this would be a very interesting question then, if the Koszul property could distinguish between these things as well, that would be, yeah, that's a very interesting idea that we hadn't thought of. Yeah. We haven't, but our colleague Andrzej Krutov in Prague with Pawle Pandzis has been working on this as well. So we're hoping to complement the two. So yeah, this is being done, but not by us. So hopefully at a later date, we'll be able to bring the two of them together. But it's a very interesting suggestion. I mean, I don't know. I've thought about, I think about this, you know. maybe, I don't know. I do think about this, you know, maybe once a year, years that go on, realize I can't say anything sensible and then move on again. But at the moment, I don't know. It would be great. Yeah.